Welcome back. Let's continue with our lecture on general theory of relativity. So far, we have seen some of the basics of tensor analysis and the invariant structures of Newton's law. So, Newton's laws are one of the very successful laws of physics and enjoyed its success over 400 years. Meanwhile, when everybody was rejoicing the success of Newton, there comes the Maxwell. Maxwell aggregates all the laws of physics related with the electricity and magnetism and combine them to write four Maxwell's equations, which are now very popular. This is one of the revolution in the physics after Newton's. Here is a first attempt of field theory in the sense here you are describing how the electric and magnetic fields are behaving, and of course you study the charge particle motion too. So that itself is not primary goal. Primary goal is to see how the electric and magnetic field themselves evolve over the time. So in this lecture we look at the Maxwell's equation and then see what are the difficulties which we arrive because of the Maxwell's formalism, or how do we overcome difficulties, and how did Einstein taken all these things to develop the special theory of relativity. Let's continue with the lecture. Let's first look at the Maxwell's equation. Maxwell compiled all existing concepts of electricity and magnetism and formed set of four equation which governs evolution of electric and magnetic field. So those are popularly known as the Maxwell's equation. The so-called Maxwell's equation, in fact, as in the case of Newton's law, you can see the Maxwell's equations also contributed by earlier people. For example, first of the Maxwell's equation, that is del dot E is equal to rho by epsilon naught, called the Coulomb's law or Gauss law. So here E is the electric field and rho is charge density, which is responsible for generating the electric field, and epsilon naught is a permittivity of the space. The second equation, del dot B is equal to 0, is popularly known as the absence of magnetic monopole or no magnetic monopole law. It's one of the most interesting thing that the electric field has source in terms of charges, where magnetic field doesn't have source in terms of charges. It's actually electric current which is give rise to magnetic field, that is reflected as a no magnetic monopole rule. In this case, B is a magnetic field. In this let's go to next law. Next law is del cross E is equal to dB by dt is equal to 0. This is called the Faraday's law. It's basically how the changing magnetic field induces an electric field. This is a rule by which all the electric generators are working, where you have changing magnetic field which is giving rise to electric current. The last of the law, which gives you del cross B is equal to mu naught J 1 by C plus 1 by C square dE by dt. So this is called Ampere's law, which basically describes how the current acts as source for the magnetic field. In this case, J is the electric current density and mu is the permeability of the free space, and the C is the speed of light, which is given as 1 by square root of epsilon naught mu naught. So that's one of the important quantity in the Maxwell's equation. The Maxwell's own contribution to this set of equation is the last term, and rest of the all equations were known earlier. That is where the rate of change of electric field is treated as a current which contribute to del cross B. So that is all combined, all forms the Maxwell equation. Now in addition, we have a continuity equation which essentially says the conservation of charge density. That charge can neither be created or destroyed, it essentially can be converted into current. So that is a main conservation principle which we have in the electromagnet. All this together forms the laws of electromagnetism electromagnetism, which we now refer to as Maxwell's equation. So here, one of the important thing to note is here the time comes as a more than parameter in this equation. In the Newton's laws of motion, we have seen that the time merely a parameter to represent the motion. In this case, it is actively taking part as a partial differential. Partial differential is quite different than taking a tangent or exact differentiation to get the velocity and such a physical quantity. So that is where the major differences come between the formalism of electromagnetism and the Newton's law. Okay, let's relook at the Maxwell's equation. One of the important consequences of Maxwell's equation is the presence of electromagnetism. After playing a bit around Maxwell's equation, presence of electromagnetic waves can be predicted. Or, in other words, to say that the Maxwell's equation themselves can be recasted in terms of wave equation, and that is very important from the perspective of development related. Let's quickly look at the derivation, how we get to show that the existence of electromagnetism. The simplest case of the vacuum solution where there are no source terms, that is no current density or no charge density, in such case we can show that the time-dependent Maxwell's equation implies the existence of electric and magnetic waves. Let's start with an equation, that is Maxwell's equation, del cross E is equal to dB by dt, and we need to take a curl of this equation on both sides and then play around them. Let's take the curl on this. We know how to do it. You might have already done in your homework. That can be simplified as a divergence of E and del square of EI. From Maxwell's equation, we can replace divergence of E as a rho. That is the first of the Maxwell's equation, and that is what we have written here. The second is essentially a Laplacian. Twice divergent contracted with each other is a Laplacian, and that is written as a del square E. The first term we can get rid of as source-free solution, that is we don't have source, so we don't have a charge density. Then we can go ahead and look at another of a Maxwell's equation, that is a del cross B. From the earlier equation, we would be getting del cross E, and that need to be differentiated. So in this case too, we can assume J to be 0 for the source-free solution, and leaving out the simplified the Maxwell's equation. Then we differentiate with respect time on both sides. What we get is del E by del T of del cross E is equal to 1 by C square into d square E by dt square. Now we substitute back everything in our first equation, and then what we get is a 0 is equal to del square E minus 1 by C square into d square E by dt square. This essentially says that electric field satisfies the wave equation, and that is what is essentially showing that the electric field propagates as a wave with the speed is equal to C. We have already seen that C can be written as 1 by square root of epsilon naught mu naught. So this is a one way is to show that the speed of electromagnetic waves independent of anything else other than two very fundamental quantities, which does not depend on the reference system. So that is mean to say that it is independent of any frame. Now the second thing is we can also show that the magnetic field also satisfies the wave equation. Algebra is very similar, and one can simply go ahead and show it without much difficulty. The next topic is to relook at Maxwell's equation and see whether they are actually Galilean invariant. We see that we have a concept of covariance where we have seen that all the laws of physics should be same no matter what the observers are. As corollary to this, what we have seen is Newton's laws are Galilean invariant, and we could have an alternative formalism of a Newton's law through the Lagrangian to make it generally covariant. But important factor here to note is invariance of Newton's law, that is Newton's laws are invariant under the Galilean transformation. So the question to ask is whether Maxwell's equations are also Galilean invariant. So that is a very fundamental question which was bothering many people. Let us go through this. One way is to simply apply the transformation rule and see what happens. That is way. But however, it is usually good idea to see terms which might create problem in advance and see which are well-behaved terms. So we have Maxwell's equation, all four of them listed here, and let's see what are the simple terms which might not cause the problem. The first ones are scalar. They rho by epsilon naught, and zeros, they transform very smoothly from coordinate to coordinate without creating much problems, are assumed to be totally harmless because they are scalar. Let's look at, are there any simple vectors? We have two simple vectors. One is 0 and j, current density. Both are vector. The 0 here and 0 here are not the same. 0 here is a scalar. 0 here is a vector. In the 3-dimensional 0 vector is a 3 tuple of 0, that is 0, 0, 0. First one is a simply scalar 0. It is amusing, but this important factor has to be recognized, that the 0 vector is different from the 0 scalar. But we know that the 0 vector is the same in all coordinate system, and we know that current density is a simple vector which can be transformed. So these two terms are unlikely to create any problem, and they are harmless vectors. Now we see that the first two equations, on which right hand sides are scalar, left hand side also have to be scalar. They are basically divergence of vector field. We know how to transform electric and magnetic field, and we also would know how to take the divergence, and divergence transformation rules are fairly straightforward, and that is what we would see, that these two terms are likely to be well defined. So these are also simple divergence or vectors, and they did not expect to create, and we do not expect them to create any problem. The next two terms are essentially curls. Curls involves epsilon ijk, which I have told you they are not tensors, so this may not transform like a tensor. However, we know how to make them a tensor by using some simple tensor analysis trick. You also might have learned that curl do not transform in a simple way. It is an axial and polar vector difference that eventually you know how to convert them into a proper vector and do the necessary transformation, and they are also not expected to create any problem. If not simple, they can be eventually made into vector. Now left with the two terms which involves the derivative with respect to time. Now this is not the exact derivative. Exact derivative we know how to transform. When you have an exact derivative, it basically transforms like contravariant vector. But this is a partial differential and not with respect to a coordinate, it is with respect to a parameter. So this might be the one troublesome term. So we need to now see explicitly put in the transformation and see how does the partial differentiation with respect to time transform. So instead of going into all beating around bush, now we have understood what is the overall problem. Where could this equation be creating the problem? Now you might have already learned previously that the Maxwell's equations are not Galilean invariant. There are various tricks used to show this. At the elementary level, you take Lorentz force equation and then come up with specific example of electric and magnetic field and show how they transform to a new coordinate system. Take a simplest example and show that eventually the Maxwell's equation do not transform properly under the Galilean transformation. However, the proper way of doing it is to take a transformation. We take transformation equation from one coordinate system xi to xi. We assume both the coordinate system are inertial. We are at present not keeping our foot on any rotating frame. So we are just interested to see how this equation transform under the Galilean transformation in the simplest form. But it is not necessary to take a simplest form where you make assumption that your coordinate system is moving with along one direction, or it is initially coincident. All that assumption which you have used, we simply use the general coordinate transformation, which we have seen that how xi and x are connected. We can invert that to get the relation between one to another and all that. The time also we can say that transform but t prime is equal to t. In the Galilean system, time do not transform, it remains same in all coordinate system. Now we just have to see what is the effect of this transformation. We are already assumed the transformation is inertial. That means that alpha ij do not depend on the position or time. That means d alpha ij dk is 0, and same way alpha ij doesn't depend on the time, so they are simply constant. On the other hand, beta I is missing here, I for an I. So what we have, beta I as vi into t into x naught I, where beta I can be written as a vi of t plus x naught I. Now, because of the inertial transformation condition, we also have a condition of velocity. Vi should be constant, do not be changing with the position or time. That is dv by dxk is equal to dv by dt is equal to 0. That is, they are constant, and x naught is a constant too. Now all we have to see that how the partial differential change from one coordinate system to other coordinate system, and then only we can write the Maxwell's equation. So we know how the partial differential transform. Our interest is mainly to figure out how the time derivative transform, but as a simple exercise, we also transform the partial differential of a spatial variable so that we see whether it is all in accordance with what we understand about the tensor transformation rule. First, let's consider d by d psi I, which is a spatial derivative in the xi coordinate system. Using the transformation and chain rule, we can simplify them or express them in terms of xi and t, and that is what we have. Note that t is still not a coordinate here, only a parameter. So once we have that d by d xi I, using the chain rule, we can write it as a dxj by d xi into d by dxj. It's a simple chain rule. We have to do that with respect to time too. This is a normal calculus, and then we can write explicitly the expression for the transformation here, and then this term is 0. Transformation doesn't depend on the time, so what we get essentially is this, which is differentiated with respect to xi, which we get as a alpha jk del ki into d by dxj. So that essentially says that it transforms like a covariant vector, so which we are already familiar that the spatial gradient which transforms like a covariant vector, and here what it says, if you calculate how covariant vector transform under coordinate system, you would exactly get the same expression. So we are on the right direction. Let's go ahead, and once we have this, we know how the gradient of a function or a partial differentiation with respect to space transform, and that is what we have earlier known. There is nothing new in that. We can easily transform any partial differentiation from one coordinate system to another coordinate system. Now we can compute the Laplacian. Laplacian in one coordinate system is basically contraction of twice gradient acting on scalar, that is taken the dot product of this with respect to g mu. Since it is a dot product, by taking the contraction with g mu nu, and we know that the dot product is an invariant under this transformation, it doesn't matter, so eventually we get the same. So Laplacian is invariant under Galilean transformation. So this is a well-known that you can easily check this out, that Laplacian is invariant under the inertial transformation. When you do it on the non-inertial transformation, some complication do happen that we will look later how Laplacian can be transformed in a generalized coordinate system. Before that, in the Cartesian coordinate system, Laplacians are invariant. Now we have to look at that how time transforms from one coordinate system to another coordinate system. Now we have to see how to compute the partial differential of a time in one coordinate system to another coordinate system. Since both t and t primes are same, we can interchangeably use, but it is not that the d by dt prime is equal to d by dt. that can never be same because of the chain rule have to be considered when you take the partial differentiation involving the transformation. So when we have chain rule and use the transformation rule from t to t prime, now we can write the partial differential with respect to t prime can be written as a dxi by dt prime into d by dxi plus dt by dt prime d by dt. So it's a general calculus rule. When you have a dependency, you just have to take the partial differential with respect to all the variables. Now we know that t prime is t. We can use that just to simplify the look. Otherwise, it does not do any good. Can use the transformation rule now to substitute for transforming from one coordinate system to another coordinate system. Then most of them doesn't depend on the time. All you get is this beta is only which depends on the time, which can be written as in terms of velocity and the initial position, and eventually we get d by di of vi into dt. Finally, we get the transformation for the partial differential of time from one coordinate system to another coordinate system as a vi into d by dxi into d by dt. So we see that this is basically divergence, and that can be written in terms of the vector notation, that is a dot product is a divergence and it is same in all coordinate system. It do not change. Those who have studied the fluid dynamics may also familiar with this type of derivative. I will not get into this detail because all of you might not have studied the fluid dynamics. Let's take this equation as we have got it and then proceed. So this partial differentiation with respect to time is a one important entity which would go into Maxwell's equation. Let's get back to me. Me is very important here. So let's rewrite them. So we know that this we don't have to worry, this we don't have to worry. Let's look at this equation or this equation and then see if both of them transform properly. Then we got to check in detail. If one of them fail, then we can simply say that these equations are invariant. Proving by example is not possible. On the other hand, disproving by counterexample is simple. All we have to get is a one case, one of these equations which do not transform properly, and then we are done. So let us go ahead, substitute this whatever we have naively learned into all these. Let's look at quantity dbk by dt prime, and now look at that d prime dk by dt after coordinate transformation. You write dbk. So first you write how the time derivative transform. There you have a v dot xi x into d prime. We still did not do anything b prime k, and then you have an ordinary differential with respect to time. Now we have to use the transformation rule for the bk. Their alpha will be involved, but alphas are constant, so they do not play much role, and betas do not come here. That we have seen earlier that they don't play role in the transforming the vector. Then the equation takes the following form. Once we simplify, it simply takes the following form. Somewhat it is not the form which we have started with. The form which we have started as a very nice equation, somehow it looks like it has become messy with the additional term. That means that some extra terms are added to this equation, which indicating that Maxwell's equations are not really Galilean invariant. So this is a very important consequence. One side you had a Newton's laws of motion, which were perfectly all right under Galilean transformation. On the other side you had a Maxwell's equation, which did not go well with the Galilean transformation. This conflict between me and me, when one of the theories does not match with the other, there is always conflict. There are people who are faithful to Newton's equation, and there are people who are faithful to Maxwell's equation, and they all fight and then get into bitter exchange and so on. Well, we don't know what happened in the history. I am not even interested in. The important point to note is here the Newton's equations are invariant under Galilean transformation, and we can extend this formalism to non-inertial frame by using the formalism such as a Lagrangian and Hamiltonian. So in other words, Newton's law is very, very successful and well established. So this success is unshaking, and which is very difficult to be challenged. On the other hand, Maxwell's equations have several problems. One of the problems of Maxwell's equation is they are not Galilean in, okay? And then forget about transforming, using the transformation and all. So there is a fundamental problem here. Now, there is another problem with the Maxwell's equation. There is a fundamental quantity which is coming in the Maxwell's equation, or when you write the Maxwell's equation as a wave equation, then you get speed of these waves given purely in terms of fundamental quantity, that is c square is equal to 1 by mu naught epsilon naught. It's a well-known quantity which doesn't depend on anything other than the nature of the free space. So what does it mean? These waves or electromagnetic waves or light, do they propagate at the same speed in all coordinate system, or is there something wrong with the Maxwell's theory, or something which is global is not always suited? You might have heard, but here there is something which is global and doesn't change anywhere to anywhere. So that is the speed of light. Is it good to have it or not good to have it? So these are some of the fundamental questions which did not seem to bother many of academicium. Only one clerk at the patent office seems to be tearing his hairs off, and then finally he came to conclusion that it is a Newtonian mechanics which require the correction, and the Maxwell's equation as they stand are correct, and we should in fact need to do a full new way of doing mechanics, what we call is relativistic mechanics, or including the proper concept of relativity both in Newtonian and Maxwell theory and consistent with the Newtonian mechanics. So the goal here is to develop a new mechanics which incorporate the principle of relativity, which is obeyed both by Newton's law and special theory of relativity. That is which agrees both with the Newton's law and the Maxwell's equation. So that is a basic idea of special theory of relativity. We will stop here and continue with this formalism of special theory of relativity in the next lecture. Let me stop here.